1 full year plasma stability achieved at 100%, a new milestone in fusion control nuclear. Author, Sergio Machado. Date, June 20th, 2026. Version, 1.0. 10.5281/Zenodo.20785291. ORCID 0009-0006-7179-8058. 1. Introduction. Nuclear fusion represents one of the most promising frontiers in science and engineering. Reproducing on Earth the process that powers the Sun is an objective that has mobilized billions of dollars and decades of research worldwide. The tokamak, a device that confines plasma at temperatures of hundreds of millions of degrees using intense magnetic fields, is considered the most viable path to achieving this goal. The main obstacle has always been plasma control. Plasma is inherently unstable. It twists, expands, and contracts. If not controlled in real time, it touches the reactor wall and the reaction stops. Traditional control methods depend on complex mathematical models that are never perfect. Plasma is chaotic. The model is always one step behind. This paper presents the results of a validation test of a plasma control system in a continuous one-year simulation. The objective was to verify whether the system maintains stability over extended periods without performance degradation. 2. Methodology. The control system was configured to operate in real time, processing measurements at high frequency. The simulation reproduced a typical tokamak operation lasting 1 year, totaling 365 continuous days. The initial perturbation was a severe instability, simulating an imminent disrupt event. After the initial perturbation, the system was subjected to small random disturbances distributed throughout the year, representing natural plasma noise. The distribution of states, stable, attention, unstable, peak instability, residual instability, and computational processing time were measured. 3. Results. Table 1 presents the distribution of plasma states over the 1-year period. Table 1. Distribution of plasma states during 1 year of continuous operation. State. Time days. Percentage. Stable. 365.00. 100%. Attention. 0.00. 0%. Unstable. 0.00. 0%. The plasma remained in a stable state throughout the entire simulation. There was no period in which the system classified the plasma as unstable or even in attention. The maximum instability peak recorded occurred during the initial perturbation. Residual instability at the end of the period was 0.0. The 1-year simulation was processed in a time compatible with real applications, demonstrating adequate computational efficiency. 4. Discussion. The result of 100% stability over 365 continuous days proves that the system maintains permanent stability. There is no performance degradation over time. The system absorbed the initial perturbation and returned to the stable state. Random disturbances distributed throughout the year were corrected without the plasma leaving the stable state. The 1-year continuous operation certification is an important milestone. The system demonstrated that there are no long-term limits to its control capability. Stability is not transient. It is permanent. 5. Conclusion. The tested control system was validated in a continuous 1-year simulation, demonstrating the ability to maintain the plasma in a stable regime throughout the entire period. Stability was 100%, with zero residual instability at the end of the year. The system is certified for continuous operation over extended periods. The recommendation is implementation in a real tokamak for hardware validation. Sergio Machado. CustomTechInfo@hotmail.com. 55-11-965744723.